we will see the questions, that questions also, the tutorial question. Along with that, we will see some new questions also. Okay. So starting with the first one. So here, the question is here to convert the decimal fraction, that is 0.1, to the binary fraction. So here, 0.1 is given. We need to convert it into its binary fraction. 0.1 is there, that is in decimal. We need to convert it into binary, and such that we should be converting. If the conversion is not exact, give the binary fraction approximate to 8 bits after binary point. So up to 8 bits we need to represent this 0.1. So so the basic method to convert decimal number into a binary is, whatever the decimal number is there, we will be multiplying it with 2, and then we will see the result. So output will be 0.2. So after multiplying, whatever the integer part is there, that we will be considering. So here integer part is 0, so 0 will be considered. So whatever the fractional part is there, we will be writing again the fractional part, and we will be multiplying by 2. So again it is 0.4. So next integer part is this. The fractional part remain is 0.4 into 2, and then it will be 0.8. Again the integer is 0. The next is 0.8. After multiplying, we will be getting 1.8, 1.6. So here integer part is 1, so that will be 1 in the decimal point. Okay. So again 0.6 multiplied by 2, and then again we will be doing is, it is 1.2, and then 1 and 1 is coming out, and then again the 0.2, again it comes 0.2, and then this path will be repeated. Again 0.2 multiplied by 0.1 multiplied by 2, and like that. So up to here it will be repeating is 0.2 will be repeating here this step. So obtained integer values are 0, 0, 0, then 1, 1, and after that 0, 0, 1, 1, then again. So this are the integers that are basically going to be repeated. So whenever a number is there, fractional number, that is, suppose a fractional number is 0.5, so it can be represented by like 1 by 2. So if any number is there, fractional number, that can be represented by the term like 1 upon 2, or 2 to the power 2 plus 1 by 2 to the power 3, and so on up to 2 to the power I. These fractional numbers will be the numbers that can be exactly represented in binary. But any other number that is not represented by this combination of 1 by 2s, okay, or 2 to the power of negative powers, you can consider. So if it is not able to represent in 2 to the power of negative powers, then these numbers will be considered as not exact. So not an exact number that is basically represented in binary fraction, or its fraction value will not be fixed. Its fraction value will be up to infinite. So it will be repeating, so it will be an infinite fraction. So similar to that is 0.1 is there. So 0.1 is, it cannot be represented exactly in binary. So here this is going to be repeated. So we can write like 0.1 will be, that is in decimal. In binary it will be 0. Then 0, 0, 0, then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on. It will be up to infinity in binary. But if we want to represent this into an 8 point, so 8 bit, so we need to represent this into 8 bit. So once we are going to represent it into 8 bit, what we do is we need to do the approximation. This approximation is called truncation. Okay. So there are different methods to do the truncation, but we will be basically using the method called rounding. So we will be considering the rounding method. So once we write it here, once we do the truncation by rounding, So up to 8 bit. So this is the first, second, third, fourth, fifth, sixth, seventh, eighth. So up to here it is 8 bit. Okay. But once we are going to round it, in rounding, so the 7 bits will be the same. 0, 0, and this last one is 1. The rounding is done between these two. So it is up to here it is, we need to consider only 8 bit. But this is 9th bit, and 9th bit is 1. Okay, so if 9th bit is 1, we will be rounding to next even number. So because this is the odd number, this combination will be an odd number. If after that we are having 1, 1, so this 1 will result to increase this value by 1. We will be increasing this 1. So after rounding, the value will be 0, and we will be adding 1 into it. Okay, we will be making it an even number. If there is an 1 beyond this range of 8 bit, we will be adding 1 into it, making it the even number. So once we will be adding, it will be like 0, 1, 0. So this will be the result obtained by rounding. So this is the result obtained by rounding. So 0.1 in decimal can be represented by this value in binary. So similar rounding we will be using while converting fractional numbers. It's mantissa, or it's basically in terms of mantissa only. So mantissa, once we are going to convert the fractional part into the exactly setting into the single precision or double precision value, so we'll be using this rounding process. So rounding is basically whenever there is 1, okay, and up to 8 bits, we need to consider only. So if there is 1 base value, so instead if this is whatever the value is there, we will be increasing it to make it even number, or we will be increasing by 1. The next question is here. So also it is not always like we have studied like single precision of 32 bit. Another one is double precision of 64 bit. But it is not always like we will be in the question. It will always be like given in 32 or 64. It may be given with some other type of representation. So here, suppose it is going to represent a 12-bit floating point representation format. In that 12-bit, 1 will be for sign, okay, and 5-bit for exponent, and for mantissa, basically it is going to use the 6 bits. Total 12 bits it is going to use. So in 12-bit floating point representation case, if this is the two numbers is given, then you need to perform is like you need to perform the subtraction and multiplication. Okay, and also here it is given like the exponent is given in 5 bits in excess 15 form. So how basically we decide like whether it is excess 15 should be there or not? So based on the number of bits. So number of bits used here is 5. So if number of bits are used in 5 base, that means the possible values, if we consider it, like what could be the possible values in 2's complement, because 5 bit is used for representing 2's complement numbers. So if 5 bit is used for 2's complement representation, so the range, when we need to find out the range, what could be the range? So range would be like minus 2 to the power 5 minus 1. So in generalized form, the range basically is written as I have already written many times. So should be doing this. So 2 to the power n minus 1, 2 plus 2 to the power n minus 1 minus 1. So this is generalized range for 2's complement number representation if n bits are used. Similarly, if 5 bits are used, then the range will be like minus 2 to the power 5 minus 1, 2 plus 2 to the power is like 5 minus 1 minus 1. So it is 2 to the power 4, 2, plus 2 to the power 4 minus 1. So it is minus 16 to plus 50. Okay. So this is range that can be basically represented in 2's complement with 5-bit representation. But when we do the analysis in case of biasing, we use the biasing to represent a single precision or double precision. Instead of using the exponent into negative numbers, we basically try to make the range of these exponent should be positive. So we should be making it positive. So once we want to make it positive, what we do is we add some numbers. So that is like, so here it is range is 2's complement range is between minus 16 to plus 15. So we will be making it like plus 15. We will be adding it. Okay. So this representation, if we are going to make it into 5-bit, so it will be represented in excess 15. So it's like excess double, a single precision is called excess 127. Similarly, this, if the exponent is of 5-bit, then it will be considered excess 15 exponent. So if excess 15 exponent, it will be represented in that form. So here two numbers are given, A and B. So if two numbers are given, we need to perform subtraction and multiplication. So first of all, we will be identifying like what this number is. So whenever this A is represented by this is the sign, and this is the exponent, and this is the multiplication. So if sign is 0, that means the A is positive number. So it is a positive number first of all. And whenever it is represented in terms of either single precision, double precision, or it is represented in terms of floating point representation, then it always be in the form of normalized form. So if it is in normalized form means once we are going to write its magnitude value or its amount value, what is it is going to represent. So it will be 1 dot. So 1 dot, this will be the mantissa or the fraction part. Mantissa are called fraction part. So we'll be putting this value here, and then 2 to the power, this is the exponent. So here exponent is this value. So this exponent is coming out like exponent e dash. That is the, with the help of, you can say, by adding the excess value. So actual exponent will be e plus 15. So after adding 15, e dash, this one will be the e dash if it is represented in excess 15. So e dash will be the exponent that will be equal to actual exponent plus 15. So the actual exponent will be like e dash minus 15. So first of all, this value is coming out to be like 0, 2, 4, 8, 16. 16 plus 1, 17. So e dash is 17 minus 15. So exponent value will be like 2. So here, this will be the actual value of A. Once we are going to represent it, that is 1 dot 0, 1, 1, 1, 0, 1, 1. So this is the mantissa or fraction part, and this is 1 dot something. 1 dot something means the number is normalized one. So always, if it is represented in floating point number, this will be always written into the normalized form only. So once we are going to represent in fraction part, we will be making it 1 dot the fraction value. So this is A. Similarly, we will be finding the B value. So B value is sign is negative. So sign is 1 means it is a negative number. So negative sign. Then 1 dot the fraction part. So this is the fraction part. So 1 dot the fraction part into 2 to the power. So this value is the exponent. So actual exponent will be e dash minus 15. So e dash is representing the 15 itself. So it is 15 minus 15. It is 0. So that's why 2 to the power 0 is there. So when in floating point representation, a number is given, you need to convert it into the scientific form you can consider. Okay. So once you are representing it in this form, now we need to do the subtraction and the multiplication. So once we go for the subtraction or the addition, the rules are same. So once we are going to have the subtraction and addition, the rules are same. It's like first we need to consider like what is the highest value of the power, or which one is having the highest to the power. So here to the power 2 is there and to the power 0 is there. So which one is having the smallest power? You need to shift this value by the difference of these two powers. So if we subtract the difference, it's basically coming out to be like we will be subtracting the higher exponent value or the lower and the lowest exponent value. So 2 minus 0 we will be doing. So it is coming out to be 2. So this one is the smallest number. So we will be shifting this value. So we will be shifting this value to the right side by 2 units, because this 2 comes like higher exponent minus the lower exponent. That will be the one we should be making the shifting. So now shift the mantissa of B. So we will be shifting the mantissa of B, that is the smaller value, the smaller number basically, to right side by 2-bit positions. So we'll be shifting this by 2 to the right side of the side. So we'll be shifting this numbers, not the bits, or we can consider this like in terms of we are going to shift. So this binary point we will be shifting this way. We will be shifting this back, or we should be shifting such that 2 to the power 2 should become. So in that way we should be shifting. So once we are shifting it here, then it will be 2 to the power 2. Okay. So we should be shifting like that so that the powers should be same. Then only we will be doing either addition or subtraction. So highest power at 2 to the power 2. This is 0. So 2 digits we need to shift. So this binary point we will be shifting to the left side to make a smaller value. So that 2 to the power it should increase to 2. So once we will be shifting it, the mantissa position will be like 0.011011010, and then this will be the mantissa, and the new exponent will be the exponent equal to the power 2. So 2 to the power 2 exponent in excess 15 will be represented by this only 10001. So this will be the new exponent of B number. Okay. So once the exponents are equal, now we will be doing the subtraction. The subtraction once we are going to do is here the two numbers are like one is positive or another one is negative, and we were required to do the subtraction. So once we are going to add these two numbers, it will be going to give you the subtraction itself. So the first number is this one, the first number is this one, this is A, and this is B. So B is the negative number, this is the positive number. So once we do the addition of these two, the overall the result will be a subtraction. So once we will be adding it, so to add it, you can just see here after binary point 6 digits are there, but after shifting the the right side of this binary point, there are 8 bits into the B. So B is having 8-bit, but it is having only 66 bits. So we need to add 2 zeros at the right side. And now we will be adding. So after addition, we have got this value. Okay. So once we have got this value, so because we have basically subtracted lower number from the higher number, the result will be the positive itself. Okay. So once it is positive, so after doing the operation, we will be again representing it into the floating point representation. So for that, so A, after doing A minus B, the sign of that is positive. So once it is positive, we will be making the sign bit as 0. And now this is in the normalized form itself. So we will be there is no need to do the normalization, because normalized it is always after the subtraction we have got the result 1 dot something. So 1 dot something means it is normalized form. So this will be the normalized form. Then this will be the mantissa, basically a fraction or the mantissa. So mantissa part. So this is the mantissa that is going to represent. So here mantissa can only accommodate 6 digits. So once it is only able to accommodate 6 digits or 6 bits, we will be considering like 1, 2, 3, 4, 5, 6. So these 2 bits are extra. So once 2 bits are extra, that means we need to do the rounding. So again, we will be doing the rounding. So once we are going to do the rounding, we will be removing this part, and once we are removing here it is 1. So that's why it will become the it will be basically considered as the next even number. So we will be basically adding 1 to this one. So the next Mantissa will be 1 1 after rounding 1 1 0 1 and then 1 0. This will be this one the new Mantissa. And the exponent, so exponent will be 2 to the power 2. So 2 to the power 2 is having the exponent value that is in plus 15 form. It is 1 0 0 0 1. So the exponent will be this. So these are the steps we need to follow once we are going to do the addition or subtraction in terms of floating point numbers. So if this is given, the floating point representation of the numbers A and B are given, we need to convert it into scientific form. And what after doing the scientific form conversion, we need to equate the exponent. So for equating the exponent, we should be shifting the binary point to the left side. This is basically for the smaller number. We need to shift the binary point of a smaller number. This is the higher number, this is the smaller number. So we will be shifting it to the left side. Once the exponent is equal, then we will be doing the operation either addition or subtraction. After doing the addition and subtraction, again we need to do like after doing this, we need to normalize. Okay, so we need to do the normalize. So steps we can just write is first of all, you need to find out the once we do the steps, what steps we can write is like first is where to first we need to make it into the scientific form. The number should be in scientific form. Once it is in scientific form, we need to make the difference of the exponent. We need to find out the difference of exponent. Then we need to shift a smaller. We need to shift a smaller number. Shift a smaller number. Right. So number or the digits should be shifting right side, or the binary point should be shifting to left side. Don't confuse it. Confused with this. So shift a smaller number right by difference of exponent, or you can write like shift a smaller number binary point left by difference of exponent. So what the difference of exponent is there, either 2, 3, whatever there, where we either shifting the digits or bits to the right side or shifting the binary point to the left side. Once we have done the shifting, then set see like add the difference of exponent to exponent of a smaller number. So whatever the smaller number is there, we need to increase the exponent of a smaller number by the difference of exponent. Once we have done this, now we need to do the operation. Perform addition or subtraction, whatever it is saying. The sixth step is after doing the addition and subtraction, we need to check for the normalizer. We need to check for normalizer. Once it is normalized, now we need to set. Once we have done the normalization, now we need to do the rounding. So these are the checks we need to perform. So sometimes there may be like the rounding is not required, or sometimes there may be like the normalization is not required, because in this case also the normalization is not required, it is pre-normalized. After addition only it is normalized. So there is no need of normalization, but These are the steps we need to check. Okay. After doing the addition and subtraction, also we need to check for the like once we have done this rounding, now we need to represent in floating point number, floating point representation. So we'll do floating point representation this next. In between, once we have done the subtraction or addition, we need to check the overflow also. After finding out the exponent also, we need to check the overflow. So for overflow, if we are going to represent in terms of like, okay, so if we are representing it into, suppose, single precision. So in single precision, basically the format is for sign, basically we use 1 bit, and for the exponent of sign 1 bit. For exponent, we are going to use 8 bit, and for magnitude it is 3 bit. Total 32 bit. So here the exponent we can consider is, so exponent could be ranging between the value that is for 8 bit, the value will be between minus 128 to 127. So this could be the exponent. Or in case of the positive numbers, if we say it, if we consider the positive numbers, it will be, it's like in terms of here, so it will be like that. In terms of the positive numbers, the exponent will be like 255 to 0. So 0 to 255, it will be basically in terms of if we are going to represent in terms of decimal numbers, so positive decimal numbers, if we find out, it will be in this range. Okay, coming out like between 0 to 255. Okay, or so once the exponent is 0 or 255, it represents special numbers. So therefore, the generalized e value, exponent value, will be between 1 to 254. So if the exponent value is between 1 to 254 for single precision, then there is no overflow. If it is like less than 1 and greater than 254, then there will be the special case of overflow. Or sometimes we have already seen like in when exponent is 0 and when exponent is 255, then what will be the numbers that numbers will call. You can just go through the PPT that I have shared. So in that it is given. So when exponent is 0 and 255, or when the exponent is coming out to be like 1, the most negative and the most positive, then what will be the number? So the basic generalized numbers will be like having exponent between 1 to 254. So next we will do is multiplication. So for the multiplication, so once we are going to do the multiplication, these two numbers are there, a and b. So once we are going to multiply, we need to add the exponent. So whatever the exponents are there, so here 2 is there, here 0 is there. So we need to add the exponent. The first is add the exponent and subtract 15 to obtain this as the exponent result. So here, because it is 15 is subtracted because it is excess 15 is there. That's why once we add the exponents, so whatever the exponents are there, it is like in this case 1 0 0 0 1, and this one the exponent. Once we add these two exponent, we will be subtracting again the 15, because after adding also it is written in excess 15. So to obtain the exact exponent, we will be subtracting the 15 from adding these two. So first is we need to do the addition of the exponent, and then we should be converting it into the e that is without exponent or without a bias point. That will be the exponent value. And then we will be multiplying the mantissa. So we need to multiply the mantissa. So mantissa value. So these two, the whole number, this one and this one, we will be multiplying it. After multiplying, we will be getting the result like this. Okay. And also in terms of sign, both one number is negative, one is positive, so the sign will be negative. So once we represent in terms of floating point representation, the result will be like the negative one. Once it is negative, okay, the sign will be negative. Sign bit should be negative, so here it is one, it should be there. Okay, and this is the mantissa. Okay, so if this is the mantissa, this is not normalized. So we need to perform the normalization. So to perform the normalization, the normalized structure is one dot this. The result should be there. So after one, there should be a binary point and then the fraction point. So but here 1 0 is the case. Or for normalization, it should be less than 2. Less than 2 is to be there, but it is greater than 2 or equal to 2 is there. So if it is equal to 2 or greater than 2 is there, we need to shift it. So this binary point should be shifted to the left side. So the normalized value will be 1.0010 and so on. Whatever the numbers of bits are there, we will represent. So this will be the normalized. So after doing the normalization, whatever is the digits, we can consider that will be the fractional part. But the fractional part could be of only 6 digits. So we'll be considering only the 6 digits. After normalization, the result is like 1 dot. So 7, 001, 011, 001, 011, this 6, and then 01. We will be writing 01. So it is up to 8 bit fraction value, but the fraction value could only be of 6 bits. So then we will be doing the rounding. So once we do the rounding, so here 3 bit and this is 3 bit. So here this is 0. If there is 0, we will not be doing anything. After rounding also, the result will be 001, 011. So that's why there is no need of rounding, because the 7th bit is basically 0. If it is 1, then we should be rounding it to by adding it 1. But if it is 0, we will not be doing anything. So the answer will be like, after multiplying a and to b is 1 in the sign, and the exponent will be like after adding 2 and 0. 2 and 0 is again the 2 exponent is there. The same exponent will be like whatever the exponent it was having. So basically, okay. So one more thing. So once the exponent, once we have shifted this boundary point to the this side, okay, to the left side, we need to multiply it by 2 to the power 1, because its value should be the same. So its exponent value will be basically increased by 1. So that's why initially it was 2. So now it will be 3. So it will be 3 in decimal. But once we add it 15, because we need to add represent it into excess 15, so it will be 18. 18 we will be representing it here. So it is 16 plus 2, it will be 18. So this is the exponent value we will be representing. So this is how the basic addition or subtraction or multiplication we can do in case of floating point representations. Also, we will see some more questions, and after that we will come to our tutorial part. Okay. So in binary floating additions we want to do, so we need to do 0.5 add with minus 0.4375. Okay, so we need to add it with the help of like a floating point addition. So first of all, whatever this representation is there, we need to convert these numbers to represent into floating point. Okay, again this one need to be converted to floating point. So we need to convert it into floating point. So by converting it into binary and then to floating point, we can represent. So 0.5 can be represented in binary as like 0.1, and then into scientific form it is 2 to the power 0 will be there. So 0.1 is there. Or we can do is we need to write it into normalized form. So this is the normalized form. So whenever we are going to perform any operation, we need to represent the numbers into normalized. It should be written in 1 point something, the fraction value. Okay. So 1.000 into to the power 1 will, because once we are going to shift this binary point to the right side, we should be making it to the power minus 1. Similarly, this number we can represent in terms of the number that is called the scientific number. Once we represented it into scientific number, and also there is one condition is, because this is not the number that can be represented in binary exactly. So here it is assuming we keep 4-bit precision. So 4-bit precision means after representing, the fractional bits will be only 4. So that's why it is only considering the 4 bits in fraction. Okay. So up to here, once it is considering only 4-bit in fractional, after shifting it, because after doing its normalization, it will be represented by like that. So these are the two numbers we need to perform the operation. Like we need to do the addition of these two numbers. So once we want to add these two numbers, so one is positive, another one is negative. Whenever we are going to add it, it will be like nothing but the subtraction is done. Okay. So for addition of these two numbers or for subtraction, we need to equate the powers. So here the highest power is 2 to the power minus 1 is the highest one. So this is the higher number. So when 2 to the power minus 1 is the highest number, we need to have the same 2 to the power minus 1 to this lower number also. So what we need to do is we need to shift this number to make it like a minus 1. We need to shift it to the digits we should be shifting to the right side, or the binary point we should be shifting to the left side. So shift here is like the significant number of number with the lesser exponent. So lesser exponent in 2 to the power minus 2 is shifted right. So we should be shifting its digits to the right side until its exponent matches the larger value. So once we shifted its digit right side, it should be 0.111 and 2 to the power minus 1 it will remain. So now 2 to the power minus 1 and 2 to the power minus 1 both are having the same exponent. Now we should be adding the significant. So once we add it, the result will be coming out like this. After addition, this is the result. So now this is the result, but we should be representing it into floating point only when it is in normalized form. So it is not in normalized form, it is written in 0 point something, but it should be written in 1 point something. Then it is normalized one. So we should be written in this form. So 0.001 into the power minus 2 can be converted into that form by doing the shifting of this binary point to the right of this one. Okay, so it is 3-digit shifting. So we will be shifting it by 3. So it will be total exponent will be 2 to the power minus 4 now. So this is the normalized form, and this is 2 to the power minus 4. So when it is minus 4, okay, and we want to represent in single precision. So here question is like we were going to basically represent in single precision. Here it is going to represent. So when it is exponent is minus 4, okay, so we need to write this exponent into the form like minus 4 plus 127. So it will be by adding the biasing. So once we are going to make it plus 127, it is coming out to be 123. So the normal range of exponent will be like 1 to 254 in case of single precision. We have just seen this is the valid range. And this 4, once minus 4 is there, by adding 127, it is 123. So 123 is coming out to be in between 1 and 254. So that is the valid number. You can say it is a valid number and it can be represented into floating point representation in case of a single precision. And then once we do the rounding, so after doing this exponent calculation and then normalization, we need to do the rounding. So there is no need of rounding because whatever the 4 bits are there, 4 bits are representing the 4 precision. This one, there is no need of rounding. Okay. Then the final representation will be like we can represent this further in terms of the decimal. If we want to convert it, then it can be converted into decimal. So for converting into decimal, it will be taking the case. So you can just see after converting into decimal, it will be coming out to be result as this. Because whatever the decimal values are there with respect to that, it will be coming out like 2 to the power like -4. So 2 to the power -4 or 1 by 2 to the power 4 or 1 by 16. So 1 by 16 is equal to this one. So this is the decimal representation. So the final result will be like either in decimal form it is 0.0625, or it will be given like the final result will be represented into floating point representation. Then you need to convert this into the floating point representation of the sign, exponent, and matrix. Sign will be here. The result is positive. Sign will be 0. Exponent. So exponent is coming out to be 123. So we will be representing 123 in binary form. And then mantissa. So mantissa coming out to be 000. So we will be representing 0000 up to 23 digits. So this will be a representation of the result into floating point representation. So whatever the steps we have done, same is given into the algorithm. This is the algorithm how we should be doing the addition or subtraction. Similarly, the next question that is basically for multiplication. So for multiplication, this is the algo you need to follow. The rules we have already gone through. You can just go through. Okay. So here the numbers are given 0.5 and this is the number, and we need to do the multiplication. So once we want to find out the multiplication, then for multiplication we have already seen in the previous question, like we should be adding the exponents. So first of all, we will be converting it into the binary. Once we have written into binary and then into scientific form, and then whatever the scientific form is there, we will be adding the exponents. And once we are going to add the exponent -1 and -2, so overall -3 is there. Once it is -3, if we can represent this -3 into 2's complement representation. Okay, so 2's complement representation will be like, if it is we are going to consider it into 8-bit format, then 3 will be 00000 1 0011. This is the 3 in 8-bit, and then we will be taking this is +3 basically. We want to find out the 2's complement, so it will be 1 0 1 1 1 1 1 1. So this will be the 3 into 2's complement. So this we can represent in 2's complement, or whatever the there. If we are want to represent in single precision, we will be converting it into positive by adding 127 to it. So we will be adding 127 to it. So overall, the exponent value will be 124. So whatever its binary representation are there, that will be the exponent basically. Once we have found out the exponent, now we will be multiplying the values. So after multiplying these two values in binary, the result will be coming out to be this one result, and the exponent is 2 to the power -3, and the result is already in normalized form. So there is no need to normalize it, but it is given like we need to use the 4-bit like precision. So once 4-bit we need to use for precision. So 1.110 we will be only the 4 using the 4-bit. So for using the 4-bit we need to truncate it by using rounding. So if we are considering the 4-bit, there is 0 only, so there is no effect of rounding. So it will be again we can write 1.110, this one. Now we can check for overflow, like whether it is overflow or underflow. So to check overflow or underflow, we need to check whether the exponent value is ranging between, here the exponent value or the e dash should be ranging between 254 to 1. If it is like that, no overflow. So it is coming out to be this. So it is no overflow or underflow. Once it is like that, we need to represent this. This is the result that is here basically. And finally, the sign. Okay, the sign is different. Both the numbers, one is negative, one number is there. After multiplication, the result will be negative. So this will the final result we will be having. We can convert it into representation by like binary, the decimal equivalent, or we can convert this into representing like floating point representation. We can represent it into the floating point also. So sign will be 1 because this is the negative number, and then we will be finding out the exponent. Exponent will be of 8-bit and the mantissa of 23-bit. So mantissa is 110. If we want to convert it into 23-bit, we will be making 110, and then the remaining bits we will be making 000. Okay, so here these are 3 bits, and then the remaining 20 bits will be this 000. Remaining 20 bits equals to 0 here in the mantissa. In the exponent it is 3 there, or if it is 3, we will be adding 127 to it, so it will be 124 positive. We will be converting 124 into, this is decimal, we will be converting it into binary. So whatever the binary equivalent will be there, we will be writing it here, that will be the exponent. This is the floating point representation of the result. So I hope you have got the basic idea of these operations. So now we will see the questions related to the tutorial questions. So in the first part, question 1, so here convert the following decimal number into binary. So once you want to convert it into binary, so it is 34.75. So 34 is the integer part and this is the decimal part. Okay, so we will be converting 34 separately and 0.75 separately. We will be taking and converting it into binary, and this one binary separate, and then we will be combining. So to convert it into binary, we will be dividing it and then find like what will be the remainder. So once we divide it, 2 1 2, 2 7 14. So the remainder is 0. Similarly, we will again divide it. So 8 to the 16, 1 is the remainder, 2, 4 8, so 0 is the remainder, and then again 2 to the 4, 0 is the remainder, 2, 1 2, so 0 is the remainder. So 34 will be represented by this 34 in decimal, in binary it will be 1 0 0 0 and then 1 0. Similarly, 0.75 is there. We will be multiplying it by 2. So after multiplying it, whatever the result is there, that is 1.5. So 1.5 is there. So 1 will be the integer part we will be considering for the answer, and the remaining fraction will be multiplied again by 2. So it is 1.0, and then 0 is there. So once it is 0, 0 into 2, it will be always 0 0 0. So okay. So after it comes 0, the fraction part, there is no need to multiply. So the answer will be like 1 and 1. So from up to down, we will be considering. From up to down, it will be considered. So 0.75 is equivalent to binary as 1 1. Okay. So the final result will be like the 34 can be represented by like 1 1 0 0 0 1 0 0.11. So this will be the equivalent binary representation. This way you can do the first all questions. Similarly, the second part is there to convert the binary number into decimal equivalent. So again, here we need to convert each other part into the decimal equivalent separately, and then we will be adding it together. So once this is the number, it is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, sorry, 0, 1, 2, 3, and 4. So that is, it is going to represent like 16 plus 8 plus 4, so 16 plus 8 plus 4 plus 0 0 0 is there, plus 0, that will be equals to like 28, and then 0 1 1. So 0 is 2 to the power minus 1. This is 2 to the power minus 2. This is 2 to the power minus 3. So we will be adding like 2 to the power minus 2 plus 2 to the power minus 3. So it is like 1 by 4 is 0.25 plus 0.125. Once we add it, it is like 0.375. So the answer will be like 28 in the integer part, and the fractional part is 0.375. So this is the binary representation. This is how we can convert it into the second part. Okay. The next one is third is perform the indicated base conversion. So for converting it into the base, first convert this of base 8 into the decimal one. So 54 to the base 8 to be converted into decimal, and then whatever the decimal is there, we want to convert it into base 5. So we will be dividing that result of this base of 10 by 5. Whatever the remainder will be there, we will be again from the top to top to bottom, bottom to top. We will be finding out all the remainders, and that will be giving you out the exact base 5 conversion. So you can perform all this. In this case, the similar is there. You need to convert it into like equivalent uh, decimal form, and then from in decimal form, we will be able to identify like which one is smaller and which one is greater. So here, question 5 is like we need to convert these numbers, decimal numbers, both in sign, magnitude, and 2's complement. So we need to convert it into sign, magnitude, as well as the 2's complement representation. So sign and 2. So if a positive number is there, the positive number will be having the same representation in the binary or the sign, magnitude or the 2's complement or the 1's complement. So whatever the representation is there, it will be having the same representation for all the positive numbers. So 5 and 2 is there, it will be having the same representation in case of like sign, magnitude, and binary will be having the same representation. But in case of sign, magnitude for -29 and for sign, magnitude in 2's complement, there will be a difference. So that difference will be like, so if we convert it like -29 is there, so we'll be making the 29. First of all, we will be converting it into binary. So 29 is there. We'll be converting it into binary. So to convert it into binary, we will be dividing it by 2. Okay. So 2 1 ja 2, 2 4 ja 8. So the remainder is 1 here. Then we will be dividing by 2 again. So it will be 7. The remainder will be 0. So again, we will be dividing by 2. So the 3, the remainder will be 1. So again, we will be dividing by 2. 2 1 ja 2. And the remainder will be 1. So it is 1 now. So we can't divide by 2. So that will be the end. Now we will be considering from down to bottom. So it is 29. We can represent 29 as 1 1 1 0 1. So this is the binary equivalent. So this is 29. So if it is like represent the following decimal number in binary and 2's complement using 16-bit, we need to use the 16-bit. So this is 1 2 3 4 5 bits only. So this can be represented into 16-bit. So if it is 5 bits are 1 1 1 0 1, 5 bits, and 6 7 8, and similarly the remaining 8 will be like the all zeros. Okay, 4 and 4. So this is 4 4 8 12 and 16. So this is like 16-bit 29 representation. So similarly, if you want to convert this 29 to negative -29, so -29 will be like the MSB bit. So this is the MSB bit. So this MSB will be indicating the sign. So if it is -29 in sign magnitude, this will be represented by like MSB will be 1, and all the bits will be like the same. All the bits will be the same. So this will be this 1 1 1 0 1. So 4 8 12 and 16. So this is -29. So only the MSB bit is 1. It will be equivalent to -29. Similarly, in case of 2's complement representation, so in 2's complement representation, this is the binary. If you want to convert it into -29 in 2's complement -29, then we need to take the 2's complement of this number. We need to take the 2's complement of this number. So once we want to take the 2's complement of this number, we will do like for 2's complement. So if it is 1, so if it is 1, it will be represented by 1 itself. And then whatever is the numbers, it will be complementing it. Okay. So this is 1, and then this one will be like if it is 0, so it will be 1. If it is 1 1 1, so it will be 0 0 0. And then it is 0 0 0 0 0. So all will be 1 1 1 1. So that we will be making it to 16-bit. So 4, then 8, then 12, and then 16. So now this is the representation of 29 minus 29 in 2's complement representation. So I hope you have got the point for the question 5th. Okay. So similarly, represent the following complement values in decimal. So this is the 2's complement is given. We need to convert it into equivalent. 2's complement number is given 1101011. So this is the number that is represented in 2's complement. We need to convert it into decimal equivalent. So first of all, if this is the number and here MSB is 1. If MSB is 1, that means it is a negative number. First of all, first this you need to identify. So if MSB is 1, this is a negative number. Similarly, the second number, if it is 0, MSB is 0, it is a positive number. You can identify directly. So once you have converted it like it is positive or negative number, now you need to find out the magnitude. What is this magnitude? So first of all, it is written like it is represented in 2's complement value. So this is a 2's complement. So its magnitude will be given by like we will be taking the 2's complement of this number. Then whatever the equivalent binary representation will be there, that will be its 2's complement magnitude value in decimal. So we will be taking its 2's complement. So once we are going to take its 2's complement, it is 1 will be as it is. Then after all the bits we will be converting. So 1 after that it will be 0 and 1, 0, 1, 0, 0. So this is the binary number. So it will be in binary form. Now its equivalent decimal will be like 0, 2, 4, 8, and 16. So 16 plus 5 is 21. So this is a negative number, but its magnitude will be 21. So it is minus 21. Okay. So similarly, the second number is there like 0, 1, 0, 1, 1, 0, 1. So this is the number, and this is a positive number because this is 0. Now we need to take the 2's complement of it. So once we take the 2's complement, this 1 will be as it is, and after that all the bits will be complemented. So if it is 0, it will be 1. If it is 0, 1, 1, it is 0, 0. Then 0, then it is 1. If it is 1, it is 0. It is 0, it will be 1. So this is the equivalent binary representation. Now we need to equate its decimal equivalent. What is its decimal equivalent? So here it is 0. This is 1, 2, 4, 8, 16. So 16, 32, and it is 64. 64 plus 16 plus 3. So it is like 60, 70, 80, 83. It will be 83. So the result will be like, sorry, one mistake I have done. So first of all, if any number is there that is a positive number and it is represented in 2's complement, then also whatever its exact binary representation is there, we will be converting it directly into the decimal equivalent. We will not be taking the 2's complement because in 2's complement or whatever complement, all the positive numbers are having the same representation. If this is represented in 2's complement, but it is positive number, it will be same as the binary number. Here I have written already like if binary number is there or if it is sign magnitude representation, if 2's complement or 1's complement, if all positive numbers are there, then it will be having the same representation. So we will be just converting it into the decimal equivalent. So it is like 1 is there, 2, 4, 8, 16. So 16 plus 8 plus that is 16 plus 8 is 24 plus 5 is 29. So it will be plus 29. So this will be plus 29, this value, the second value. So I hope you have got the point. So if any number is there that is represented in positive form, then either it is 2's complement or it is 1's complement or it is binary or it is sign magnitude, its representation will be same in positive case. But in case of negative, once we have identified like it is a negative number because MSB is 1, then we need to take the 2's complement to identify its magnitude. So now sign is okay. So we have converted it to sign that is negative, but its magnitude will be given by taking the 2's square. The next is assume numbers represented in 8 bits 2's complement representation. So the calculation of the following. So here we need to perform like 6 plus 30. So here the similar is like we need to convert these numbers into the 8-bit 2's complement representation. So first of all, 6 is there. So if it is plus 6 will be having the representation in same as binary, and the 2's complement will be having the same because it is plus 6. So if it is plus 6, we will be representing it like we need to represent it into 8-bit. So 6 is like 110 in 4-bit. This is we need to convert it into 8-bit. So we will be making it 00. So this is plus 6. Similarly, we need to convert it into minus 6. If we want to represent it in minus 6 in 2's complement. So whatever the 6 is there, this is the 6. We need to take the 2's complement of it, then it will be converted into minus 6. So we'll be taking 2's complement. So for taking 2's complement, so whenever we will be counting the first one from the right side. So here it is 0. This is the first one. We will be putting as it is, and then whatever the numbers are there, we will be complementing its value. So once we will be complementing it is 1, so it will be 0. Then it is 0, then it will be 1, 1, 1, 1, 1. So this will be the minus 6. Similarly, if we want to find out the plus 13 into the 2's complement. So plus 13 in 2's complement or 1's complement or the binary representation will be same. So it will be like this is like 8 plus 4 plus 12 plus 1 is 13. So 13 is there. If we want to convert it into 8-bit, we will be adding 4 zeros here. So this is plus 13. Similarly, if you want to find out the minus 13, so minus 13 like we need to convert it in by taking the 2's complement. So we will be taking the 2's complement of this. So first one is this only. So we will be keeping add as it is, and then we will be complementing all the bits. So it is 0, so it will be 1. If it is 1, 1, it is 0, 0. Then all the 4 zeros are there. So 4, 1 we will be putting. So this will be the minus 13. So now, so once we have converted all the numbers, then we need to do the 6 plus 13. So once we want to do the 6 plus 13, we will be adding this 6 into 2's complement and then 13 directly. Once we add it, the result we will be getting. Similarly, if we want to find out like minus 6 plus 13, so minus 6 this one plus 13 this one, we will be adding these two. Similarly, 6 minus 13, so again this 6 minus 13 we will be adding it, and then minus 6 and minus 13, minus 6 and minus 13 we will be adding it. After addition, we need to find out also to check for overflow. If we are going to check the overflow, so there is a rule also, just go through it. What is the rule for checking the overflow? I have already told you the slides, you can obtain that. So basically, when the overflow will occur, the overflow will occur only when the sign of these two numbers. So whatever the two numbers we are adding a subtraction, doing the subtraction, or what we are going to add two numbers, if the numbers are having same sign, then only there is a chance to have an overflow. Okay, so once the numbers are having the same sign, then only there will be an overflow. The overflow occurs like if it is 8-bit representation, there will be no need to check overflow, because overflow will not be taken because it can accommodate all these addition results. So you can just go through the overflow rules also. Okay, so whatever the rules are there. Next one is find the following difference using 2's complement. So if two numbers are given, you need to find out the difference of these two numbers using 2's complement method. Like this is the one number, this is another number. You want to subtract this number from the first one. Okay, so once you want to subtract it, so instead of subtracting, what you can do is you can take the 2's complement, the second number, and then we can add the first and the 2's complement of the second one. Similarly, you can do same for all, and also check for overflow. Comment on overflow. The next numbers are like x is equal to this one, y is equal to this one. In 2's complement notation, this is the 2's complement notation. Okay, and then its equivalent, decimal equivalent is 5 and minus 6. So here you need to do the product of x and y using Booth's algorithm. So with the help of Booth's algorithm, you need to find out the product of these two. So we have already gone through the example into the class, like how we can proceed through the Booth's algorithm. There is a flow diagram is given, and also the hardware is given. Hardware used for designing the Booth's algorithm and the flow chart. Just go through hardware and flow chart, and in the flow chart, whatever the steps are given, just follow the steps. You will be getting the result. Okay. And similarly, multiply each of the following pairs of kind to complement number using this algorithm. In case, in each case, assume A is okay. So here again, we need to do the both algorithm multiplication for both these numbers combination. Okay. Use both algorithm to multiply 23 by 29, where each number is represented using 6 digits. So okay, so here it is given each number is represented into 6 digits. You need to use the both algorithm to multiply these two numbers. All are having the similar structure. Okay. Next one is divide 145 by 13 using both restoring and non-restoring division algorithm. So in the division algorithm, we have already seen different methods. So these are basically for fixed point. Okay, so these are for fixed point numbers up to this. So here we need to perform the division of 145 by 13 by using the restoring and non-restoring methods. So just go through it into the restoring and non-restoring methods, and then you will be able to identify. So first of all, you can do is 145. What will be its binary? First, we will be doing is binary representation. 145 into binary, and then 13 into binary. So you need to make sure like whatever the number of bits are there here, similar number of bits should be here. And also the similar number of bits should be there into the accumulator register. So you need to identify like how many bits are there into 145, and then similarly you're going to make it into 13 also, and the accumulator content will be also having the same number of bits. And n value will also be the count value. Whatever the number of bits will be there, that will be the count value will be equal to the same. That much will be the count value, number of bits basically. Then just proceed through it. So you can get answer. Yes, the next one is represent the following numbers in IEEE 32-bit floating point representation. So it is -5 is there. So you need to represent. So this represent what is this representation is there in 32-bit floating point representation. Basically, the representation is there. Like one sign bit is there, one exponent will be there, and one mantissa will be there. So in 32-bit representation, sign will be having 1 bit, exponent will be of 8 bit, and mantissa will be of 23 bit. So you need to represent this all these numbers into this form. Okay. So what will be the sign bit, what will be the exponent bits, and what will be the mantissa bits. So similarly, just go through it like -5. So if it is -5, we have already seen in the previous class, this starting of the class also. So if it is -5, you want to represent it into this floating point representation. Okay, in single precision. Then what you need to do is you need to first convert it into binary. Okay, so you need to convert it into binary, and also is like if it is -5. Okay, so if it is -5, so for representing negative sign, there is a separate bit. So you can just take only the +5. Okay, so you can make this sign bit as 1 into the representation, and you can now convert this 5 to binary. So binary it will be 101. This is in binary. So this 101 is the number you need to represent in scientific form. So if it is scientific form, it will be 101 into 2 to the power of 0. This is scientific form. Now this is in scientific form, but you need to represent this number into 32-bit floating point number only when it is in normalized form. Now we need to do the normalization. Once we do the normalization, it will be of the form like 1 dot the same. Okay. So we will be making it 1.01 into 2 to the power. Once there is no boundary point, means the boundary point is here. Now we need to make this boundary point at this location. So we are making 2 digits. So we'll be increasing this by 2. This is the scientific form of in normalized form. So now if it is in normalized form, we need to find out the sign. Sign is negative already. Exponent. Exponent is +2. Exact value. Once it is +2, we can represent this exponent as it should be of 8 bit. So +2 is like in 8 bit, it will be like 4 bit, 5, 6, 7, 8. This will be the +2. And then Mantissa will be 0, 1. So 0, 1, that will be a 2 bit, but we need to have 23 bit. So 21 zeros we will be adding. The total it will be like 23 bit. Then we can represent these values into here. So without bias, the representation will be sign bit will be 1. The exponent will be like all this 0, 0, 0, 0, then 0, 0, 1, 0, 1, 1, 0, and then the exponent like Mantissa will be like 0, 1, all zeros, 23 zeros. This will be without bias. If we want like with bias, so with bias, what will be the changes? Only the sign, the value of this exponent will be changing in with bias. The sign bit will be same. The Mantissa will be the same. The exponent value. Exponent was 2. With the bias, we will be adding the new exponent. This new exponent will be e plus 127. So it will be 2 plus e was 2. 2 plus 127. So it will be 129. So 129, we will be converting it into binary, and this binary value we will be putting it into export. So this will be the new exponent e dash. So this is the with bias, or we can write like it is excess 127 representation of floating point. Similarly, you can do for all these numbers. First of all, you should be converting it into binary. So whatever the sign is there, sign you need to separate it. Only consider the positive part. In the representation, sign will be changed to 1 once it is negative. Otherwise, it will be positive. Once we have converted into binary, now make it into scientific form. Now do the normalization. Once we have done the normalization, we need to represent this exponent without bias and then with bias, and then represent it into the form. This is the basic one, how you can convert. Similarly, here the reverse process you need to do. The 32-bit floating point representation is given. You need to find out the equivalent decimal value. So you need to find out the equivalent decimal value. So here the sign bit is 1. So if sign bit is 1, that means this number is negative. This is 0, 0 means this is positive. Also, you need to place value. So whenever the number is given, you need to consider it as like it is given in bias form, like it is given in excess 127 form. So if it is an excess 127, whatever the exponent is there, you need to, that exponent is e dash. You need to subtract, find out the exact exponent. To find out the exact exponent. What you need to do is e will be e dash minus, like it will be plus 127 minus. So whatever the exponent is there, you need to convert it into decimal, and whatever the decimal is there, you will be subtracting 127 from the decimal. That will be the exact exponent value. Okay, and then you can convert it into, and the remaining part is Mantissa. You can convert it into the decimal form, equivalent decimal form. Okay, so the next question is, what would be the bias value for? You need to find out the bias value. So how we find out the bias value is like, what would be the range of numbers, the range of 2's complement numbers for that particular representation. So if here a base of 2 exponent is a 6-bit field. If a 6-bit field is there, that means exponent is represented by basically 6 bits. That means exponent can have the range like it is going to represent the positive and negative numbers. So it will be having, we need to find out the 2's complement range basically. So 2's complement range for 6 bit is minus 2 to the power 6 minus 1, 2 plus 2 to the power 6 minus 1 minus 1. So it is like minus 2 to the power 5, 2 plus 2 to the power 5 minus 1. So it is minus 32, 2, 2, 4, 8, 16, 32. 32, and this is plus 31. So here it will be like plus 31 excess 31 would be the bias value. Basically, the bias value will be 31. So in the second case, it's like it is of 7 bit. So if it is of 7 bit, in the 7 bit case, it will be minus 2 to the power 7 minus 1, 2 plus 2 to the power 7 minus 1 plus minus 1. So it is minus 64 to minus 64 to minus plus 63. The bias value will be here is 63 basically. So these are all the basics. Okay, so the next part is basically to perform the calculations. Okay, so you need to do the multiplication. So this is one floating point number. This is another floating point number. You need to do the multiplication of these two. So this is all about the second unit.